once again, there are seasons in the operating systems industry where they get ahead of themselves. And it would appear that some of the newer versions of OS that have rolled out, in particular the 22H2 version of the Windows operating system, especially in the server side of things, WSL is not really ready for prime time yet. And so even though we've had successful implementations in previous seasons with CSC 410 students, and they've been able to integrate Linux with an enterprise file system in the final module, what we have now is a case where there's a new version of WSL, WSL2, and it turns out that while they have implemented WSL2, they have not yet released versions of Linux that can be implemented for the WSL2. So you need to use older legacy methods to install WSL manually and install as a WSL legacy setup. And we're getting mixed results. So in some cases, some server OS can implement and others can't. In my case, I ran into a number of inconsistencies with my server proper. So when I was running troubleshooting attempts to resolve my own WSL inconsistencies and errors, I basically ran into what I call a tipping point, where I could not get my system to behave reliably in the virtual environment. And so I wiped the virtual machine out and started from scratch and rebuilt my server 2022 VM on the local machine. And you see here that if you mouse over, you start to get clarity on the menus, but you have to intentionally mouse over in order for that stuff to display correctly. There are still some glitches they're working out between VirtualBox and 22H2 on the server OS. The license that I attempted to activate with Microsoft, it's the same license that I have off of our Microsoft downloads. It basically said that it was installed previously, and I'm either going to have to get ITS to help contact them, or I'll need a VPN connection to the campus or be on campus to attempt to activate, because even the manual commands to activate return a message. So that's kind of frustrating. In any case, if I were in your shoes and I were performing this activity, I'd have plenty of error messages to capture to submit for the screen. I wanted to see if anyone else had similar or different experiences. So if we could just take a moment, could you, now, if you haven't had a chance to get to this yet, simply tell us that you're still working on some availability this week to get to it. But I'd like to hear from the rest of you. Ladies first, Shanoa, were you able to successfully implement WSL on your server VM?
Yeah, like the WSL.exe.
Mm-hmm.
Yeah, I didn't run into no problems.
Did you follow the article that was linked here?
Yeah,
Okay. And that worked okay. So you were able to submit for the assignment showing like an ls command in the WSL prompt?
yeah.
Outstanding. See, hit or miss. All right. Well, I'm glad that this method worked. Petri, by the way, is an invaluable resource online for Windows Server implementation and troubleshooting. And it's, I would put Petri on the same level as Manassi. Have I ever pitched Manassi's book with you in this class?
I don't recall.
Okay. Mark Manassi was commonly regarded as most valued professional and MVP in Microsoft circles, very similar to Russinovich for sysinternals. Mark was the first to come out with a definitive reference for the Windows Server operating system when it first came out, and had been writing since it was known as Server NT, NT Server, New Technology Server, which was a different animal, did not include a directory-based enterprise scalable infrastructure, but with the advent of Server 2000, lightweight directory protocols, and so Kerberos and LDAP became the critical pieces that allowed Server to scale up to a full enterprise globally. So you could install a single domain using the Server operating system. Windows Server domains, a single domain for the United States Army was implemented at one point. And we're talking about 2 million systems in a single Server 2000 domain at one point. Pretty amazing thing. But Manassi was considered to be the definitive expert, sort of an Albert Einstein in his field. The thing that distinguished Manassi from all other authors is that he had a sense of humor, and he wrote in very understandable prose, and he revised his Server 2000, Mastering Windows Server 2000, for each version that came along, 2003, 2003 R2, 2008, 2008 R2, 2012, 2012 R2. He's basically revised each edition. It was true at one point that you could simply buy his volume, read the volume from cover to cover, all 1,400 pages of it. You could walk into a testing center and certify as a Microsoft Certified Systems Administrator just by reading his book. These each became bestsellers, which is an amazing thing in the computer world. The fact that you'd have like the equivalent of a New York Times bestseller for nerds. I'm sorry, that's just not something you see every day. And I know I'm kind of playing this up, but if you can pick up a used or reconditioned version of Mastering Windows Server 2012 R2, that's the last book that Manassi had a hand in writing. And if you want to understand problems and issues that you face in the Windows Server arena, oftentimes you'll find an answer there where you can't find one anywhere else. Now, I did not include this as a required textbook for our course, in part because, well, our chair is fond of dinosaurs, and he grew up and cut his teeth on Silvershots, and Silvershots is the, well, he's the computer science reigning champ when it comes to generic operating system principles. So if you have a copy of the Silvershots Dinosaur Volume Edition, 10th edition, you basically have 3 decades of legacy with Silvershots. But the concepts are framed in generic terms so that you can extrapolate to either Linux or Unix or Mac or Windows environments regardless. Let's hear from the other two real quick, and then we'll pivot and get into our material. We've heard from Luke and Shanoa. Tell me, what was your luck with WSL? Were you able to implement WSL?
So my WSL version says version 2, but I was also following the instructions to set it to default version 2. I don't know if I still had to do that since my version is 2, but when I did that, it's giving me a virtualization error. Basically, I have to set it to virtualization, but I didn't have any luck with that.
Okay. Did you capture any error messages and submit those?
Yeah.
Okay. Shanoa, did you set yours to WSL2? Or did you, I mean, do you remember doing that in your implementation? Because that was also my experience. It's like there was a tipping point. Every time I turned to WSL2, it seemed to go sour.
I'm not too sure.
Did you follow the steps verbatim?
Yeah.
Okay. Well, there you have it. So it works sometimes and it doesn't work other times. Deanna, would you mind sharing with us about your experience?
Yeah, sure. So I followed the instructions as well. Everything was going fine until I had to install the Ubuntu. I don't know if that's how you pronounce it.
Yes.
When I put into the command, it said that the installation failed for mine.
Great.
And then when I clicked to install, I think I put in the command to install, it was giving me the list of commands. But I have the screenshots in my submission that you'll be able to see.
Right. So if you follow these steps, when you issue the first command, it actually sets it up. But for some of us, when you issued that first command, instead of installing, it basically gave a list of options.
Right.
As if you were typing a help command. Which would tend to suggest to me that there's some back-end disconnect between components. There could be some DLLs or some version control issues that are playing out where some of us are meeting with success and it flows like the Petri article. And then in other cases, it didn't. I appreciate everyone taking a moment to share their own experience. I will post credit promptly for this assignment. And what I'd like to do for the rest of the time we have today is to finish up our review of memory management. And I'd like to start with the highlights. So I plucked some things out of the slides, and I'm probably going to make a habit of doing this more for the remainder of our semester. Can everyone see
Professor,
Yes.
I just have a quick question. So for the same submission that we had, would you still suggest that we delete the VM and start over and see if there are any changes?
I'm going to try to resolve the activation registration issue, and I'm going to try a couple of things after our class. At this point, I'd say don't do that.
Okay.
If it turns out that our Microsoft Downloads only allows us to install one virtual machine in an entire year on one instance only, I'd like to take the hit on that myself as the instructor of the course instead of afflicting all the students. There are other things we can do with your standalone machine, and in order to implement Linux in an enterprise environment for our next module, instead of offering an option that involves WSL, we're going to pivot and set up a virtual machine with a basic Linux variant, and simpler the better. But it seems that Ubuntu has a broader population of support. And so what we might do for the next module is basically ask each of you to toss your server standalone. We might ask you to delete your server standalone VM and then load up an Ubuntu VM instead. Now, I haven't made a final decision on that yet, so I'd like to ask everybody to hold off on making any changes or deleting or rebuilding. But I wanted to share with you the depths of troubleshooting and frustration I reached on my own machine, and I'm running a business class ThinkPad, and I'm pretty squeaky clean when it comes to the variety of, or the mix of applications on my business laptop. So it blows my mind that so many students have so much gaming stuff on theirs, and then they report problems. I'm like, dude, you have to uninstall Steam. Don't uninstall and rebuild your server. Just unload Steam, please. Anyway, it's another conversation. Thank you for asking that question. I'll let you know before the day is out. I want to try something as soon as we're clear of the screen. Can everybody see my screen now?
Yes, we can see it.
Yeah.
Yeah.
So I want to hit the high points, right? And so I just want to call out some slides more so than others. When you hear the term paging in an operating system, we're talking about mapping physical frames. So a chunk of physical memory is referred to as a frame. And logical memory allocations, chunks of logical memory allocations are referred to as pages. And so when you're working paging in an operating system to manage your memory, you're essentially overlaying logical pages of memory on top of physical frames of memory. That's the takeaway for this slide, right? So we want you to understand that concept in terms that are just that plain, right? So the physical address space of a process can be non-contiguous. And that's the thing that we want to call out, and why paging is such a necessary memory management concept. Any questions about this?
None for me.
So here you see logical memory pages, and here you see the physical memory frames. And can everybody see this component in between, referred to as the page table, right? When you talk about critical components of paging capacity in an OS, the page table it's really kind of like the PCB in process management. Can anybody remember what the name of PCB is, the acronym stands for? Anyone? What does PCB stand for in process management? It was just a couple of weeks ago. A critical and central. Say again?
The process control block.
Yes, thank you, Luke. The process control block is a central and critical component to process management. Process control block is kind of like a repository, a centralized repository of critical information. In like fashion, the page table serves a similar purpose, right? Here you see the page table, right? And so a page table is going to have cross-references or indexed the logical memory pages and the physical memory frames. And so in this simple example, if you have page 0 to 3 on the page table, page 0 is at frame number 1, page 2 is at frame number 3, right here. Page 1 is at frame number 4, and page 7 is at page number 3. Now, why wouldn't it be like 0, 1, 2, and 3 It could be that the logical memory size has to fit in a different fashion or manner. A lot of it has to do with sequence of memory writes and the intentional choices of a user, right? So there could be priority applications that are demanding more memory frames on the physical level, and so they take up those first. So it could be a prioritization issue, it could be a size issue, but instead of seeing page 0, page 1, page 2, and page 3, I'm just calling this out intentionally. You notice the first available frame on the physical memory is page 0, but the next one is actually frame 4 instead of frame 3. And then 2, and then 3. The important thing is that logical overlay would simply not be possible without this critical piece in the middle of the page table. So think for processes, it's the PCB that's kind of like a critical piece in the middle of everything as it's flowing. And then for memory, the page table. Any questions? So here's a more explicit example of the same thing. You have logical memory pages, you have physical memory frames. And so here in the page table, page 0 is stored in page frame 5. So A, B, C, D here, frame memory and bytes and where those byte boundaries are, that's another part of the process. So the reason this looks different is because in this example, we're talking about address range and byte boundaries. So the 5th frame may include this particular component or this particular segment of physical memory in the frame. Okay, that's why it appears differently. Any questions about this deeper example? So this last piece, this last slide that I'm going to share, we want to call out is this concept of a translation look-aside buffer. You have challenges with memory management. And yeah, the page table is stored in main memory. Page table base register points to the page table. So this is a critical register in the process. So where do you find the page table? You look at the page table base register, and it tells you where to go to find the page table. Page table length register indicates the size of the page table. So you have a starting point, then you have a size, and between the two, you can tell where it starts and how big it is, right? But essentially, you have two memory access problems that can be solved by the use of a special fast lookup hardware cache called the associative memory or translation look-aside buffer. TLBs are equivalent to the term associative memory. You'll see both used. Let me repeat that. You'll see a reference in many cases to either term, which is talking about the same animal, a special fast lookup hardware cache. We talk about special fast lookup hardware caches. Does everybody remember L1, L2, L3, static RAM, super fast hardware caches on a motherboard and on the chip from computer architecture? On a broader scale, when we're talking about the chip and the motherboard, you have special fast lookup hardware caches that should ring a bell. Level 1, level 2 are usually found on the CPU itself. Level 3 is usually found near the die on the package, so it's in the vicinity of the chip, but not exactly on the CPU itself. And that's like a higher level kind of cache, but within memory itself, you have special fast lookup hardware caches called associative memory or TLBs. So it's a similar concept that's implemented in physical memory. Does anybody have any questions about how a concept similar to L1, L2, and L3 cache from CSE 241 plays out within memory hardware itself? Going once, going twice. Okay. So let's make sure everybody can see my screen. Where are we here? Can everybody see this?
Yeah.
Okay,
Yeah.
good, because sometimes when I'm moving my Zoom bar around, it suddenly stops sharing, even though it says it's sharing. All right. So from our last class, we mentioned that memory management includes this concept of partition. Memory partitions are allocations of memory that include boundaries, right? Much like a disk partition. So essentially, wait a minute, let's go back up here. There are challenges to partition allocation and page and frame memory allocation. So essentially you have these three scenarios. Let's examine each quickly. How to satisfy a request of size n from a list of free holes. Does everybody understand that term free holes? Based, and I'm not talking about frijoles in a Mexican restaurant. Free holes. I'm sorry, that was a poor attempt at humor. Just seeing if you're awake. Free holes, that's a reference to the chunks of memory that are sporadic and appear to be randomly placed in the memory frames. The diagrams we just saw. Does everybody understand this idea? That you're going to have free holes of memory frames on the physical level. So first fit, you just allocate the first hole that's big enough. Best fit, you allocate the smallest hole that is big enough. Worst fit, allocate the largest hole. Does everybody understand the distinction between those three concepts?
Yeah.
Okay. So in that previous diagram, I said sometimes it has to do with size. Sometimes it has to do with sequence. We're dealing with size issues and sequence issues. You take the first one that comes along in the sequence. Boom, you're done. First fit. Best fit, you're allocating most efficiently. So you want to find the smallest hole or smallest frame that can accommodate the interest. It produces the smallest leftover hole, so it is the greatest efficiency. But of course, you got to look at all the holes and determine which one's the smallest, right? That's part of the process. There's overhead associated with this approach. Worst fit, allocate the largest hole. So we're just going to pick the biggest one to be sure. It's the fastest. This one's the slowest, generally speaking. This one is the fastest. Well, actually, this one's the fastest. The first one to fit it, boom, regardless of its size. Yeah. So which one's going to post storage sooner? The first fit, most likely. Okay, because you have to take a look at all of the different frames. Best fit would be the most tedious, worst fit would be the quickest. Just pick the largest and sling it, but you have the largest leftover hole. First and best fit better than worst fit in terms of speed and storage utilization or storage efficiency. So I know this is kind of a obvious thing, but if you had a module assessment item that said, which of these is the least efficient? And not, and in terms of utilizing available memory, and it's not the fastest either. You'd say worst fit. Does anyone wonder why they even have that option? Why would that option even exist? Can anyone think of a reason or a rationale why it would still be good to have that in the mix? I'll give you a hint. It has something to do with priority. Okay, fragmentation. When you're stowing chunks of memory in different holes that are organized in a different sequence, you're going to have fragmentation. So external fragmentation is when you're talking about the frames, right? So the total memory space exists to satisfy a request, but it is not contiguous. Internal fragmentation means allocated memory may be slightly larger than the requested memory. This size difference is memory internal to a partition, but not being used. First fit reveals that given n block allocated, loss to fragmentation, 1/3 may be unusable. So these are two cases where fragmentation occur, and would anyone care to guess which is likely to have less overhead in terms of the description that's provided here? Would anyone care to guess which of these two fragmentation options would involve less overhead for an operating system, given the description?
Internal.
Yeah, I agree.
Yeah, I agree with internal.
Internal would be more efficient in terms of utilization, but external would be faster, I'm guessing. That might be worth researching a little further. So internal fragmentation inside a memory partition would have its advantages. External, anytime you, so the short answer is anytime you do something where you can work hardware instead of internal machinations or internal gymnastics, anytime you can work more directly with hardware, there tends to be a performance gain and less overhead. I mean, there are exceptions to that, but and virtual memory would be one big exception to that. But in terms of working with physical frames, yeah. Okay. We'll see if we can research and answer that question. But here you see 1/3 may be unusable, 50% rule. So of course, writing outside of the partition to reduce external fragmentation. Memory compression is something that's been around a long time. So it used to be that when PCs were were just breaking onto the scene, you could load an application into your boot disk that would engage an application to compress the contents of RAM, and then use RAM as a RAM disk. So you'd use RAM as a disk instead of the actual floppy disk to improve performance. And of course, yeah, there were trade-offs in performance. So whenever you're dealing with compaction to reduce fragmentation, you're still dealing with a lot of I/O. So what's the takeaway from the slides we've been seeing is that there may be strategies to better utilize memory, but each one has its own trade-offs. When we talk about the backing store, we're talking about virtual memories, right? So you have disk fragmentation with a backing store. So wherever you have gains, you might have losses in terms of I/O bottlenecks. It all depends on which one's better for a given system. Well, it depends. If the server has hardware that is specialized for I/O, then this kind of hit would not be as big a problem. So that's where operating system tuning comes into play. The idea that you can work different methods for memory management based on the physical hardware for a given platform, that's where the really cool stuff happens when you're dealing with system administration and engineering issues. Red Hat has kernel loadable modules where you can take advantage of the hardware capacity, and so for a given physical configuration, one approach would be very much better in terms of the trade-offs. So what are we saying? Half the trick for tuning an operating system when it comes to process management, memory management, disk management, all of that is to understand the interaction with the physical layer and to see if the trade-offs are reduced based on whether or not your specialized hardware makes up for that. So has anyone ever heard of a disk controller, like a RAID controller?
That sounds familiar.
Yeah, you have specialized hardware that does high performance I/O with disks, and it actually has additional memory caches, and it's usually installed in an expansion slot where direct memory access is possible. So you have with direct memory access, you have reduced bottlenecks because the disk to memory translations can happen directly, more so than through the CPU. So DMA is a huge innovation. Disk controllers are a huge performance innovation when it comes to server memories where there's a lot of disk reads and writes. So, and everyone remembers what RAID stands for, right? Redundant array of inexpensive disks, something like that. Okay. Segmentation. So another memory management method. We were just talking about paging and such. Segmentation is another concept that's helpful with memory management. In particular, it's something that is adapted and well suited for the user layer applications. So it's further away from the kernel. And there are logical components that ultimately interface with physical components, right? So this would be like an API level kind of approach. With segmentation, you have a common block, stack, arrays, and a symbol table. So in terms of the user, you have and developer, application developer, you have memory allocations that are framed with did you guys do any of this in your CSC 242 class? Data structures? Please tell. Please.
I remember the stack. We covered the stack when I did data structures.
Okay. Thank you.
Yeah, I was gonna say that all I remember is the stack.
You remember terms like stack and heap and all that, right?
Yeah.
Okay, cool. So memory segmentation is another convention where you have a logical view of the segmentation. You have the user space and then you have physical memory space, right? Kind of a repeating theme here though, right? You see user space and then over here you have physical memory. And it's a bit like the pages and the frames. So, yeah. Of course, you have those critical components in order for segmentation to work efficiently. In the same manner that you'd have a page table, you have a segment table, right? And the idea there is similar in nature to the page table. So you have a starting point and then you have an end point. The distinctions are similar, right? You have a special memory allocation for the segment table base register, and then a sizing attribute that tells you how big it is, right? Kind of a similar strategy. You have protected memory and so the challenge is that there's a dynamic storage trade-offs. When you're working logical overlays of physical memory and you're working with user applications, yeah, the way this is handled works very differently than paging memory, right? So you have your base and your limit and your segment table, and then your physical memory. And so you have allocation of physical memory based on this this piece of work here. Any questions about this diagram? So referring back to paging, physical address space of a process can be non-contiguous. Divide physical memory into fixed blocks called frames and pages. If this doesn't ring a bell, you haven't been paying attention for the last 30 minutes because I called this out about 15, 20 minutes ago. It's like one of the slides you should commit to memory. So in any case, yeah. The page table, there's just more information about the page table. We're not going to spend a huge amount of time on a lot of the in the weeds detail about this. It's the main concepts that I want you to be most familiar with. This is significant right here. This bullet point, and we could call this out a little more. The size is power of 2. So your your frames, physical frames, can range inside from 512 bytes, which is 1/2 of a kilobyte. Does everybody understand that?
Yeah.
Okay. So just for giggles, a megabyte is 1024 kilobytes. So if I have 16 megabytes times 1024, I get 16,384. But my smallest unit of measure for physical frames could be as small as 512 bytes. So essentially what I can do is take these kilobytes and multiply by 2. So what does this number tell you? In terms of memory frames, you can scale from 1/2 kilobyte to as large as 32,768 times that size, all the way up to 16 megabytes in terms of frames, right? 16 megabytes may not seem like a big deal, but let's do a little more math. Let's take 4 gigabytes. Okay. 4 gigabytes is a laptop with is there anybody here that has a laptop with less than 8 gigs of memory? Anyone? Does everybody have pretty much a laptop with 8 gigs or more? All right, let's say your average laptop is 8 gigs. Don't answer that question if you don't want to. All right, so you have 8,192 megabytes. So divided by 16 megabytes. Why am I doing this? If I take a laptop or a PC with 8 gigabytes of RAM, and I'm working paging using the largest frame size possible, I can have up to 512 very large frames. Or I can have 16,770,216 frames of 1/2 kilobyte. Does everybody understand how I got that number? Basically just walking through some math.
Yeah.
Yeah. So that's quite a bit of variability when you think about it. And when you think about it, is it possible to work some OS internals where your deliberate selection of page sizes matters? Oh yeah. Depending on the nature of the application that you're working with, the size of the data that you're crunching, you can fine tune an operating system so that it's very much more efficient. In layman's terms, it's like deciding whether or not you're better off having small delivery trucks or an 18-wheeler or a super freighter, right? So those are relevant considerations, you know. That's why the page table is so important. So how many entries do you have in a page table? Well, that would depend in part on the number of pages you have, right? So your page table can be smaller and more efficient, or very large, and a lot of overhead depending on what's going on with your OS. And this is some of the internal mechanics of that page table and addressing scheme, page number and page offset, right? So it helps you identify location and size. A lot of CPUs have dedicated hardware for paging and for memory management. And so a lot of this is processed in hardware instead of as an OS internal. This is the example we saw before of the paging table. So process management, think PCB, memory management, think paging table, right? Or segmentation table, if you're working something in user memory management, right? So here's some other examples of other calculations, similar in nature to the ones we just walked through, right? And based on the calculations for your given scenario, you can anticipate how much fragmentation. That's one way you can make informed decisions about, or the OS makes informed decisions about which options. Solaris supports 2 page sizes, 8 kilobyte and 4 megabyte. So, wow. So a lot of OSs give you a range of size, but Solaris says 8K and 4 megabyte. And that's because most Solaris systems are very large. They're server class machines. You do have some workstations that run Solaris that are pretty powerful. Is everybody familiar with Silicon Graphics, SGI? How about Jurassic Park? Everybody's heard of Jurassic Park, yeah? The movie?
Yeah.
Yeah.
Okay, a competitor with Solaris was a company called Silicon Graphics, and they had similar types of workstations that were high-powered graphical workstations that were used for rendering special effects for movies. And one reason the industry exploded and prospered as much as it did is because of its connection with the entertainment industry and special effects for Star Wars, for Jurassic Park, and all the other cool stuff that you see all the time. A lot of that has to do with the fact that these high-powered workstations and servers for rendering special effects had enhanced memory management, simplified memory management, high-performance memory management. You could correlate simplified with high performance if you had the right sizing interests in the mix, right? So relative to an office worker with a desktop that juggles, 15 different office apps, and the size of files you're rendering are very much smaller. So when you think special effects, think large media files, huge media files, gigabytes of media files. It's a different dynamic altogether, and that's where your memory management comes into play very, very strongly. So here's, just an example of this Solaris memory allocation, right? And if you're dealing with 4 megabyte pages, those are large pages. We've already mentioned the high performance hardware cache. It has 2 names that both mean the same thing: associative memory, or TLBs. So I'm going to throw these acronyms at you in your assessment. I'll say PCBs and TLBs, and you got to be able to pluck out TCBs as the high performance. Now, the size of high performance physical memory is much smaller. Static RAM is very expensive, so it's not as plentiful. So high performance associative, right? Associative memory or translation look-aside buffers. That static cache, that static RAM cache. A lot of times that high performance memory is very, very costly. So they're small, but they're used over and over again very fast, right? So small but high performance. Think crotch rocket Kawasaki or Porsche 911, or better yet, Bugatti, Lamborghini, take your pick. Not so much a tractor trailer truck, but a very high performance, smaller kind of thing. So it says some entries can be wired down for permanent fast access. Wired down meaning, yeah, literally what it says, hardwired, right? What would be a good example of a performance enhancement on a gaming laptop or a gaming PC? If you're dealing with a high performance gaming PC and you have expansion slots that accommodate multiples of graphics cards, you could have some physical accommodations that are intentionally designed to increase performance. So, any questions so far? So if you have an address translation P and D, one reference has to do with the page, the other one has to do with the frame, right? Which of these do you think has to do with the page? I'm sorry. It's not a trick question. Obviously. Are you still with us? We're almost done. So paging hardware with TLB. What does TLB stand for? What is it? Quick? Anyone? High performance associative memory. That would be your answer. So if I show you this picture in module assessment item and I say, what does TLB, what term below is associated with TLB? If you see associative memory, that's your one, right? Everybody with me?
Yeah.
Okay.
Yeah.
Okay. Excellent. And TLB is the page table equivalent for the use of that associative memory, right? No, I'm sorry. That is the TLB. That is the associative memory, and here's the page table. My bad. Sorry about that. Okay. So yeah, this is the cache to the side. That's the main physical memory. These are RAM modules in the DIMM, and these are high-speed cache, right? So what's the takeaway? Oh, you have page tables for associative memory, just like you have page tables for physical memory. Lots of calculations to determine effective access time. I'm not going to spend a lot of time or ask you to be able to calculate that kind of stuff. Yeah, not in this module. Memory protection. Memory corruption is a thing, especially with servers. This is a quick, final, but important topic. You have to be able to validate the content of memory, and you have to be able to protect memory, especially in cases where there's high number of very rapid read writes to memory frames, and physical memory can really have huge problems. Servers that support thousands of users simultaneously run into problems like this. So memory protection is a big consideration for server operating systems in particular. So that's something that's a critical aspect of memory management in a server operating system. The fact that you have additional bits, it's often referred to as buffered memory. When you have extra bits that are used to signal whether the contents are valid or invalid, whether they've been corrupt or they are preserved, that bit, that extra buffer, that's the extra buffer provides the bit of memory. That's literally what I mean. Yeah, the bit of memory to signal yes or no, 1 or 0, valid or invalid. That's the part of buffered memory. You also have something called error correction and control. That's ECC memory. It's similar to buffered memory. Valid or invalid bits. So this is a way of logging the validity of the memory content as it's being thrashed, right? Shared code, private code, and data. So memory integrity becomes that much more of a concern with shared memory. And here's an example of shared pages in physical frames versus logical. Multitasking, multi-user, right? So when you have multitasking, multi-user processes that are sharing a common base of code and content, shared pages add an extra layer of challenge for memory integrity. And so there are additional criteria that are included to validate how well that stuff is flowing. And here you see page table hashing, inverted page tables. There's all sorts of techniques to work memory integrity methods, hierarchical page tables. Let's say that again. These are methods that help ensure the integrity of memory, hierarchical paging, hashed page tables, and inverted page tables. Each of these allow for a before and after comparison. So if you want to, like a view from 50,000 feet, what are these things? What are they and what do they do? Each of these methods allow a before and after comparison of memory content. That's the intent, right? So hashed page table, you know that whenever you're doing hashes, you have a before and after calculation, yes? Everybody's familiar with that intuitively at this point of your senior status? Hashing before and after, if they match, you're good. Everybody?
Yeah.
Okay. All right, very good. Yeah, multi-level paging table scheme. So you have this cross-reference before and after, yeah. Two-level paging example. That's what they're going to the trouble of doing here. So one of the things that I'd like to share with you is that although 64-bit processors are prevalent, a 64-bit logical address space is not a normal thing, except in supercomputing environments. Normally a 32-bit logical address space is the stuff that is commonly worked. 64-bit logical address space is ginormous. So if we're finishing up this module, the last thought that we want to encounter as the clock runs down in the last 2 minutes of our class, right? Look at the size of this thing, right? So 64 bits, 2 to the 64th, right? You run into all sorts of challenges with just the sheer size of this thing. So your CPU has to keep up with huge amounts of memory. A page table has 2 to the 52nd entries. If you get out your calculator, turn it to scientific mode and do y to the x as a function, right? To calculate how many page table entries there are. That is a crazy number of, so two-level paging schemes aren't sufficient. You run into all sorts of like integrity challenges when you run 64-bit unless you have specialized hardware, again, supercomputing, high performance scenarios, right? 3-level paging scheme, hash tables. Let's keep going here. Inverted page tables. Yeah, each of these allow for before and after comparisons. So a Solaris Oracle Spark is a high performance workstation / server. Think Silicon Graphics and special effects again. So these are very expensive machines. When I say very expensive, I mean 50,000, 100,000, $250,000 for one of these, right? Not commonplace, not the kind of thing that we see, right? CPUs are 64-bit. It's called IA64, Intel, but also AMD, right? Pentium CPUs were 32-bit, IA 32-bit. There are translation schemes for memory management in Windows operating system. It's called WoW. And that's just a side note, a benefit, right? So there are cases where you have to translate between 64-bit applications and 32-bit applications to accommodate new performance scenarios. And so you also have overlays between 32-bit and 16-bit. So yeah, this is information about the 32-bit architecture. I'm going to summarize this for your study guide and addendum, just to catch the high points that you need to know about. And so there are differences in the paging architecture between 32-bit address ranges and 64-bit address ranges, just because of the scale, right? So, by the way, whenever you see this reference right here, unless you see a 64 in the mix, usually x86 means 32-bit. If you see x64, that means 64-bit. I don't know if you're aware of that yet, but if you ever see references to operating systems and they talk about x86, that's usually a 32-bit address range. ARM architectures. So when you're looking at RISC chips, memory management is a little different. Once again, I'll go ahead and extract the primary concepts out for you in the study guide. Any questions before we clear for the day?
I'm good.
Okay, well, I look forward to Thursday. We'll finish up our review of virtual memory, and then we'll go ahead and post a module assessment, and then get ready for our file system and disk module. That'll be our last great dive into operating systems. It's kind of a favorite, save the best for last.